Welcome to this video on diffusional mass transfer. Here we will have a look at strict analogy between heat and mass transfer, specifically for the transient 1D case. Let me just pick here my laser pointer. And what we will do is we will review the solution of the 1D heat conduction problem as it's sketched here. However, the transient one, we will understand the steps that led to the solution, then try to carry over or to apply the knowledge from there to the diffusional mass transfer case. So diffusional heat transfer, diffusional mass transfer. Let's have a look at the setup. Here we have a so-called semi-infinite plate. Semi-infinite means it has a start, that's the left side here, but actually typically no end. However, this is mathematically defined, and you will also see in a short amount of time what it means if a physical thickness of the plate can still mean that it can be solved with methods derived for semi-infinite plate conditions. So we have here temperature plotted on the ordinate. We have the spatial coordinate shown here. The differential equation to be looked at is indicated here with a dependency on time and spatial coordinates. Here we only plot spatial coordinates, so time may be a parameter. And solving this is difficult as we have a partial differential equation. Using the right transformation, we can get to an ordinary differential equation where the variable eta now depending on both x and t. Theta is the non-dimensional temperature difference as shown here, and it's built on the initial temperature, which is indicated here as T0 with a dotted line, and the ambient temperature, which is here is shown here, and it's also the surface temperature on this left-hand side. The solution is already shown, it's tabulated in our manuscript. However, for which case does this apply? Well, the boundary conditions here in T and not in theta, let me go through those. The temperature at the beginning, regardless where in the plate, is T0. That's indicated, as I said, by the dotted line. The temperature for any time except 0 at x equals 0 means that this left surface is T ambient, shown here. And the temperature for any time and x going to infinity is T0. Means very far to the right the temperature is T0. However, to make the plate semi-infinite, we have to request that the temperature on the right-hand side surface of the plate remains at T0 when we use this solution. The moment T0 is the temperature here is deviating from this value, we cannot apply the solution anymore. Now let's also have a look at the left-hand side. If we prescribe the ambient temperature at the surface of an object, here the plate, it is equivalent to saying that the heat transfer coefficient, the convective heat transfer coefficient, is infinity. Now let's move forward and have a look at how the temperature profiles inside the plate look like with increasing time. So we have first, that would be the original one, a rectangular step, and then as time progresses, we get a flattening of the temperature profile. As I said, in the moment where this deviates from T0, we will not have an applicability of that solution anymore. Now let's do some heat flow estimation, because typically we are not so much interested in the temperature profile inside an object. However, we are interested in how much heat is going into the object, how much does it take in. So q dot 2 primes at x equals 0 means at the left-hand surface. That's according to Fourier's law. Here lambda times temperature gradient at this position, and it's the negative gradient. If we put that in, derive it from the previous solution. There's the driving temperature potential and this prefactor, which can be calculated as lambda times rho Cp divided pi times T. Now, if we now go to the mass transfer equivalent and try to carry over the elements from the heat transfer, then the setup is the same plate. Now our variable is xi, and here it's still the x coordinate. That's xi ambient of component E, that's xi initial of component E, and our equation is shown here. If we divide by density, we get here d xi I dt equals diffusion coefficient times second derivative of xi I. And if we ask for a strict analogy between heat and mass transfer, we can replace d by the thermal diffusivity. However, we will not focus on that one in this little video, so let's stay with this equation. And again, having the same substitution, but now with d instead of a, we can use the same equation, eta, and here it's no longer theta, the non-dimensional temperature difference, that's xi, capital Xi, the non-dimensional mass fraction or mass concentration difference. And the solution is sketched here. 4 boundary conditions is written down here. That's xi I at the beginning, anywhere in the plate, that's xi I 0, indicated by the dotted line. Xi I for times larger than 0 at the left-hand surface, xi I ambient, as I have shown it here. Xi I for any time larger than 0 and x going to infinity is xi I 0. That's the semi-infinite boundary condition, saying that we have to maintain the right-hand side of the plate at xi I 0, then we can use any plate as and consider it as a semi-infinite object. However, when the concentration here would deviate from the initial value, then we cannot lose the solution anymore. How does this solution look like? We get similar profiles than for the temperature before, now for the mass fraction. And we are, of course, interested here in what kind of diffusive flux or diffusive mass flow is entering that plate. So that's chi dot 2 primes at x equals 0, and it can be equated as shown here. And this is the driving potential. Now let's compare this to what we have seen for heat transfer. So that's this formula just talked about, and here you see the formula for heat transfer. Difference is the potential has a unit, Kelvin here. Here it's non-dimensional, and this group gives then something that is 1 over Kelvin times Kelvin, and then we get watts per meter square as q dot 2 prime. And here also please check the units. The shape of the curves, if we maintain the correct scale, will be absolutely identical. So if we have a strong analogy, we can use basically our derived formula for heat transfer and just have to be careful to replace lambda or thermal diffusivity by the corresponding properties for mass transfer, watching out that here the potential is non-dimensional, here we have Kelvin in the potential. This brings me to the end, and some questions you should be able to answer. First one is related to that semi-infinite boundary condition. The second one is to review all the boundary conditions and to make you think about which ones are the critical ones to be taken, for example, at the left-hand side of the object. And at the left-hand side of the object, what does it mean if I'm saying that the surface temperature or mass fraction is identical to the ambient one? With that, I hope you enjoyed listening, and see you soon.